So welcome to this second lecture on chemistry, topic by topic. We're going to have a look today at the structure of the atom. So we're going to have a look at basically what is an atom made of. So let's have a look. Well, the basic structure of an atom is something like this. You often see these in the periodic table, and we get a mass number at the top and an atomic number at the bottom, unless, of course, your periodic tables ran the other way, because there is no real hard and fast rule about which one goes where. We have basically a larger number and a smaller number. The larger number is the mass, and that's the number of protons and neutrons. And then we have the other number, which is the atomic number, which is the number of protons, and it's also the number of electrons. So if we have a look at lithium, it's got 3 protons, it's got 3 electrons, and we see from the number there, it's 7 minus 3, which is 4 neutrons. Okay, so what we often get asked to do is to draw an atom of something like lithium. Right, so where do we start? Well, there's some rules of doing this, and many students learn them as the 288 rules. Now, we have to be able to draw these, but probably simpler to start with looking at this a slightly different way. And what we're going to do is we're going to use a little bit of equipment which you might find sort of helps and makes life a little bit easier. So if I just grab hold of a piece of equipment, let's have a look at it. So we're going to look at lithium 7, 3. Let's remember those. So here I have a piece of equipment, and inside I've got some bags of various different bits and pieces. I've got protons, I've got some neutrons, and I've got some electrons. So let's have a look at what we've got. Lithium has got 1, 2, 3 protons, and it's got some neutrons. So let's put those in. These are going to be blank. So I've got 1, 2, 3, 4 of these. Now, they don't have to be arranged in any particular order. The atom's perfectly capable of doing that, and we don't need to worry about that. And then let's look at the number of electrons we have. We've got the same number of electrons as we have these protons. So we've got 1, 2, and we only get 2 in the inside shell. And then we've got another one in the next shell. So there we have lithium. Right, so can we have a look at some more of these? Yeah, very simply. Let's choose another element on the periodic table, and we'll have a look at that. And an obvious one to have a look at is probably carbon. So let's move that one out of the way, and we'll bring in a different one. So let's have a look at carbon 12. Now, carbon 12, it's got 6 protons. So 1, 2, 3, 4, 5, 6. We've got 6 neutrons. So let's just put those into place. And then we've got to have the 6 electrons. And the 6 electrons we have 2 in the inside shell, hydrogen, helium. And then we have another 4 in this other shell. So lithium, beryllium, boron, and carbon. Now, many people, when they try and draw this, they tend to try and put these electrons together in little pairs. And the reason they often put them in little pairs is they're easier to count for no other reason than this. Some people will argue that these electrons have got to be equally spaced, and that is true. But this is only equally spaced in a 2-dimensional model, whereas in fact, in a 3-dimensional space, it's going to be different. And perhaps the electrons don't look like little plastic counters, so they may well be different than this. Let's look at a different atom. So we'll look at a little bit further along the periodic table. So let's just move that one out of the way. And I'm going to bring in my periodic table. And here is my periodic table. Fortunately, it's got quite a lot of reflection on it. Now, we've got hydrogen, then helium, and then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And for GCSE, you need to know up to the first 20 elements, really. And people say to me, well, I don't really need to know this, do I? Because I'm going to be given one in an exam. Absolutely true. However, there is a little problem. So when someone says, can you find me mercury? We go along, we try and find mercury, and it's not easy to find because mercury up here is a different symbol. It's Hg, and it's not as obvious. This is in fact a piece of mercury oxide. And this is a very nice little periodic table which consists of a real piece of each of the elements. Some you'll notice are missing. They are the radioactive ones, and I wasn't particularly keen on having those. More of the periodic table is available though here. Sometimes we wonder why the periodic table is sort of done like this, and it's basically to put it into a smaller space, because if I put all of these bottom elements in those 2 spaces there, then this periodic table is going to be really wide. So let's have a look at another element, and I'm going to have a look at fluorine, which has got 9 protons. So let's have a look at that. Let's bring in what I've got, and I'm going to need 9 protons. So I've got 6 in here at the moment, and I'm going to want another 3. And if we look at the periodic table for fluorine, the number for fluorine is the relative atomic mass is, well, I happen to have one here, and let's zoom in on that. So fluorine is 18.99 to be very accurate. We're going to call it 19, and we'll talk about why that's not a whole number in a few minutes. So we've got 19. So if I've got 9 protons, then we're going to need 10 neutrons. So I've got 6 at the moment, and we're going to want another 4. So let's just get these out of the bag. And there is our molecule of fluorine's nucleus done. We've got to get the electrons right now, and so I need another 3 electrons, and this is why we put them in pairs, because it's so much easier to try and count them up, and because they go round here, they're not all orientated the right way. And there I've got an atom of fluorine. It's got 2 electrons in the inside shell, and we've now got 7 in the outside shell. We move along the period until we come to neon, and neon here has got an extra proton, and the number of neutrons is 20. So we've actually got the right number of neutrons there, and what I'm going to do is put my extra electron in here, and now we have got a full outside shell. It's the electrons that do the chemical reactions, and because this is now very stable, we find elements like neon are not very reactive at all. In fact, writing a book on the chemistry of neon is probably one of the most boring books, because it doesn't really do anything. We'll do one more of these, and now I'm going to look at an element of sodium. I'm going to move that one out of the way because I'm going to want that one in a moment, and we're going to try and make sodium. Now, sodium on the periodic table is about to be delivered to me. Sodium on the periodic table here has got 11 protons, and this is where my model starts to run into some severe problems, because we've got to try and get 11 protons in here. So I've got 3, 6, 7, 8, 9, 10, 11, and the number here is going to be 23. So let's zoom right out. I went the wrong way. And so if I've got 11 here and we've got to get to 23, I've got to add 12 neutrons. So I've got 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, it doesn't quite fit in here. It's a little problem that I have with this. Right, let's sort out the number of electrons that we need for this. So we've got sodium, and if we look at this back on the periodic table, sodium is in the 3rd row, the 3rd period. So I've got 2 full shells and then 1 other electron. So let's look at this. So we've got 2 full shells. So let's just put in my electrons for here. And now we've got 1 extra in the next shell. So we've got a model, a way of trying to produce some atoms. Now, you won't be asked to use these sort of models in a question, you'll be asked to do it a different way. So let's have a look at a different way of trying to do this. So if we look at here back to an atom of lithium, we've got the nucleus. Around that, we've got 2 electrons, and in the next shell, we have 1 more electron. And these are called dot and cross diagrams. Let's have a look at carbon. So I'm going to look for an atom of carbon. And looking at an atom of carbon, we can see that this has got 2 electrons in the inner shell, and I've got 4 electrons in the next shell. Unfortunately, circles aren't one of my best things to draw. Let's move along, looking at now an atom of fluorine. Fluorine has an interesting spelling. The number of times I see flowering is, well, very high, I suppose. Fluorine, we've got 1, 2 electrons, and 1, 2, 3, 4, 5, 6, 7. We looked at an atom of neon. We have electrons in the outside shell. We have a full layer there, and we have another full shell. And the last one we looked at an atom of sodium, symbol Na. And we've got now another full shell. And in the outside, we've got just 1 electron. Now, this is where we bring in some interesting properties, because if we compare this with the atom of lithium, they're in the same group. And so we see a common property here. And the common property is that in simply group 1, we've got the same number of electrons in the outside shell. Now, what does this mean? Well, it's the electron in the outer shell that's actually doing the chemical reactions. So if they've both got 1 electron in the outer shell, then we can expect these atoms to react in the same way. Let's then take a look at what we've learnt so far. We've got the number of electrons, we've got the number of protons, and by and large we can ignore in these dot and cross diagrams the numbers of neutrons. So we don't need to worry about those too much. But now we move on to another problem of ions, atoms, and isotopes. So let's have a look at those and see how we can make some sense of what is an ion, what is an atom, and what is an isotope. And we'll start by having a look at simply what is an ion. I've got here quite a complicated atom. So I'm going to make this one a lot simpler, and we're just going to go and have a look at lithium. So I'm going to take out my neutrons and protons and give me just the 4 neutrons and the 3 protons and the 3 electrons I need. So this is an atom. When an atom becomes an ion, for something like here, this is lithium, we are going to lose one of these electrons. Let's have a look at that on a piece of paper. I've got an atom of lithium. So my lithium atom with its 3 electrons, and if we look at an ion of lithium, then what I'm going to do is I'm going to just draw this now with 2 electrons. But to show something's happened, we normally put it in brackets, and I've now managed to lose an electron. I've lost a negative. It's 0 charge. We've managed to take away a negative, so this becomes +1. It is an ion. Let's move along and have a look at a different atom and see what we can do with that one. Let's take the atom of sodium. If we take the atom of sodium, it's got 2 electrons in the inner shell. We've got a full next shell. And in the outside shell, badly drawn, I've got 1 electron. And as we'd expect for the ion of sodium, we're going to have the inner shell complete, the next shell complete. My circles really are getting worse. And because we've lost 1 electron, we don't have that other shell. And because we've lost 1 electron, it is now plus. We'll do one more atom to have a look at, and we'll look at here an atom of something easy. Let's have a look at magnesium. Magnesium's next to sodium in the periodic table, so it's quite easy to work out the number of electrons. 2 in the first layer, 8 in this second shell, but this time it's got 2 electrons in the outer shell. When magnesium forms an ion, it loses 2 electrons. So we get our first 2 shells complete. So this ion of magnesium looks very similar to the ion of sodium, especially from its electronic structure, but it's lost 2 electrons, so this is now 2+. The difference, of course, is not in the electronic structure, but the difference is that magnesium has an extra proton than the sodium, and that changes its properties of it as an atom. So that's making an ion. Let's now go and have a look at what is an isotope. So we've made atoms. Let's make some isotopes. And I'm going to start here with something very, very simple. I'm going to start with hydrogen. So here we have an atom of hydrogen. It has one proton and one electron. But what would happen if I gave it an extra neutron? So now we've got exactly the same chemical properties. It's still got one electron. It's still hydrogen because it's got one proton. But the atom is much heavier. We call this, in fact, deuterium. Very few isotopes have names, but one that does is hydrogen. Deuterium we use quite a lot in chemistry for analysis. There is another version of hydrogen which has two extra protons, two extra neutrons. These make tritium, an isotope of hydrogen. It's got now one proton, two neutrons, and only one electron. This substance is rather sort of heavy, and it spontaneously breaks down to give us an extra proton and an electron, which is thrown out at high speed. This is a radioactive element, and pretty dangerous it is too, and so tritium's not widely used in chemistry. It's used instead in various other things where we need radioactive items. So let's have a quick look at some of these isotopes. One of the most common of the isotopes is that of chlorine. We know chlorine has two isotopes. We've also got here hydrogen. That's well known for its isotopes. And another one, carbon. That's well known for its isotopes. Let's go and have a look at these in turn. We'll start with the easiest one, hydrogen. Hydrogen has got a proton and one electron, and this one electron whizzing round. We can have this one proton plus another neutron with this little electron going round, and I'm going to call this deuterium, and we can have the third one, which is tritium. Now this diagram's not very good, is it? Let's see if we can see how we could write it out easier. We write the chemical symbol hydrogen. It's got atomic mass of 1 and it's got 1 proton. That also tells us we've got 1 electron. Deuterium, same symbol for hydrogen. We've got 1 proton but 2 neutrons. And tritium, same symbol because it's hydrogen, 1 proton, but this time we've got 2 neutrons plus the 1 proton, giving us 3. So these are our 3 versions or isotopes of hydrogen. Let's look at carbon. Carbon is again fairly similar. We've got 2 electrons here, and we've got 1, 2, 3, 4 electrons in the outside layer. So this is carbon. It's got an atomic mass of 6, of atomic number of 6. It's got its 6 protons, 6 electrons, but it's got an atomic mass of 12. That tells us it's got 6 protons plus 6 neutrons. You won't be surprised perhaps to realize there's another version of carbon, carbon 13. This will have 6 protons, but it's got 7 neutrons. And there's a third version of carbon, carbon 14, 6 protons, and this time 8 neutrons. And this one is unstable, so therefore it is radioactive. Not all elements are radioactive. It's just some of them are. Let's finally go and have a look at chlorine. So we'll have a look at the element chlorine. So chlorine, I haven't drawn this one out, so we'll do this one, has 2 electrons in its inner layer. In its next shell, it's got a full shell. And in its outer shell, it's got 7 electrons. Let's look at chlorine. So chlorine comes with a peculiar number. If we look chlorine up on the periodic table, chlorine comes with a number that I wouldn't quite expect. Chlorine here comes with the number 17, but instead of having a whole number, we've got a number which is about 35.5, which we find in most textbooks. So what does this mean? Well, in fact, there are 2 isotopes of chlorine. And the 2 isotopes are chlorine 35 and chlorine 37. And this gives us a bit of a conundrum, because which one am I using? Well, when we look at this in real life, we find that we've got an interesting situation. The situation that we've got chlorine 35, and that makes up about 75% of the amount of chlorine. The other version, chlorine 37, isn't as common. It makes up about 25%. We need to try and work out its mass, and we can do this in a fairly easy way. We can take our number, 35, multiply this by 75, and then we can add this onto the other mass, 37, times the 25%, and then if we all divide that by 100, we come out with about 35.5, which is our number for chlorine. So we can work out the masses, the isotopic mass for different elements if we need to. Let's have a look and see what we need to look at next. So there's our atoms and our isotopes. We've talked about, we've got hydrogen in its different forms, but too many neutrons makes the elements unstable, and so this can cause quite a few problems. So where are we in looking at what this is doing? Well, I want to look at one more little topic before we finish, and I want to start by having a look at something called moles. We use moles a lot in chemistry, and we simply use moles because they are a measure of the amount of substance. So rather than saying necessarily I've got 5 grams of sodium, I might say that I've got 0.5 moles of sodium. They aren't true, they're not connected. We can look at all of these. So let's take, for example, a particular element, and let's take an element here of sodium. Now, sodium has got a mass here, and if we zoom in, you can see, of 22.98. That's a bit difficult to try and work with, so I'm just going to call sodium a mass of 23. If I take 23 grams of sodium, I have 1 mole of it. If we look at magnesium, then magnesium has got 2412. So if I take 24 grams of magnesium, this is 1 mole. Let's see if we can look at that a little bit more sensibly. And here, right, that didn't do what I wanted it to do. Right, okay, here I've got 12 grams of carbon in a little container. 12 grams of carbon. Now, if we look at what the structure of carbon is, then carbon 12,6. Here we're using the top number, so we've got 12 grams of carbon here equals 1 mole. Well, let's grab a different substance. Let's grab hold of some sulfur. So I've got some yellow sulfur in here, 1 mole of sulfur, which is a mass of 32 grams. So if we take the element sulfur and 32 here, sulfur's atomic number, if we just grab the periodic table here to have a look at, we can see here we are, some sulfur down here, and it's got a number of 16. And for many of the lower elements, we often find that these numbers are half of what we want. So 16, 32, 6 and 12, 12 and 24. Yeah, they don't always work. 23 and 11, but we'll work on this. 32 grams of sulfur equals 1 mole. Now, that doesn't seem right, because if I take these two substances, I've got an enormous amount of sulfur here, and I've got a small amount of carbon. But the interesting thing about this is that 1 mole of any substance contains, building the excitement here, the same number of atoms. And that's quite an interesting sort of thought. So, how many atoms are in there? How many atoms are in there? And we had a guy called Avogadro who worked this out, and he worked out there were 6.02 times 10 to the 23 atoms in 1 mole. Now, that number doesn't mean anything to most people, so let's just put that one in perspective. I'm not particularly good at drawing a map of the UK, but let's think about it. What is 10 to the 23 atoms? So let's go to a beach, and we look on the beach and we're looking at the number of grains of sand. Are there 10 to the 23 grains of sand on a beach? And some of you will say, well, I can think of a really big beach. And the answer is no. It's a lot bigger. All right, so it's bigger than that. Let's look into the sky and let's count the number of stars that we can see. And again, no, nothing like that. So instead, let's take a map of the UK. All right, let's take the whole UK and we'll cover it in sand. Is that 6 times 10 to the 23 grains of sand? And the answer is no, it's not. Now, what we've got to do is we've got to pile the sand up about, I think it's 100 and I've forgotten the number now. That's terrible, isn't it? 1,500 kilometers, 150 kilometers, 1,500 meters. It's an enormous number. My assistant is just looking it up for me. It's an enormous number of grains of sand, and it sort of really puts things into perspective about how big a number like 10 to the 23 is. And we think of that in there, this carbon. I've got 10 to the 23 atoms in there. So that takes us through basically the structure of an atom, and hopefully that gives you an idea about that. We've looked at then ions, atoms and isotopes, and we've had a brief look at electronic structure. Next time we're going to have a look at the periodic table, its history and its development, and how things work with it. And some of that's quite good fun. So I'll see you then. Thanks for watching. Goodbye.